We're going to start now. I want to go back over this. We finished this with last lecture looking at the warming and cooling curve because now we're going to use all these baby Qs. And remember, like we said, Dalton's law of partial pressure. This is very similar to that. We know Dalton's law of partial pressures told us that the sum of the partial pressures of each of the gases in the tank will add up to the total pressure. The same is true here. The sum of all my baby Qs will give me my overall baby Q. And so I walked through these yesterday, but let me give you another diagram. This isn't in your notes, so this is something you'll probably want to copy down, be able to take a look at. I'm gonna on my left-hand side, on the left on the y-axis, excuse me, that's my temperature in degrees Celsius. On the x-axis is the heat added in joules, and we increase as we move to the right. And I'm going to take you through a diagram showing you all 5 of these baby Qs. So the first one, we're going to start at negative 20 degrees. We go up to 0. Now, remember water. We're doing this for water. So water is going to have 2 flat lines. One is melting point, and the other one is boiling point. So we're going to stop at 0. Now, my ice still as a solid. It's still as ice. It's just warming up. At 0, I pause because now I go from 0. I go into my first flat line. But first of all, let me go with this. This is my first baby Q, and as you see, the line is at an angle, therefore it's changing temperature, therefore you have your delta T, MC delta T. But then I flatline, and as I flatline, now I'm going through a phase change. None of the energy is going into a temperature change, it's all going into the phase change. And I'm changing from a solid to a liquid, and this is mass times latent heat of fusion, or enthalpy. It's also called enthalpy of fusion. So my regular chem I said HFUS, for honors chem we say latent heat of fusion. Means the same thing. So if you see it, I'm leaving it here because if you see it on the state tests, you won't be confused. Latent heat of fusion, enthalpy of fusion, same thing. And then once all of my ice is melted and changed to a liquid, then my liquid starts to increase in temperature again. Now I have another Q, and this is a Q we dealt with a lot. When we originally dealt with MC delta T, we stayed in this range, ranging from 0 up to 100. But you see we're going through a temperature change, so there's another MC delta T. Once I get to 100, my water starts to boil, and so it flatlines here. The water, once it starts to boil, does not get any hotter, like I mentioned before. All of the energy is going into a phase change, not a temperature change. So now I start to go from a liquid to a gas, and now I have another unique baby Q, and this is mass times latent heat of vaporization, or enthalpy of vaporization. They mean the same thing. Once all of my liquid is changed to a gas, then my gas, or the steam, or liquid, the water vapor, will actually start to get hotter and hotter and hotter again. In this situation, now I change in temperature again, so I have my third MC delta T. Now, all the specific heats, I do provide them for you, and I will always provide them for you for all the substances. For specific heat of water, there are 3 of them. For gas, it's 2.02. As a solid, it's 2.06, so as ice. And as a liquid, it's 4.184, and you've been used to that. Now, I want you to see this diagram, kind of understand what's happening with my energy in terms of delta H, exothermic versus endothermic. As I'm moving up my chart, as I'm moving up from a solid and moving up all the way to a gas, I'm actually having to take in heat to get warmer. Therefore, as I move up the chart, it's an endothermic reaction, and my values will always be positive. However, as I move down the chart, go from a gas now all the way back to a solid, now I have to get cooler, and to get cooler, I must lose my heat. So a great way to remember this is just think about your body. Your body, again, gets hotter, it absorbs heat. When it gets colder, you lose heat. It's a great way to understand, again, whether your answer is going to have a positive or a negative sign behind it. And again, the highest temperature of liquid water is actually 100 degrees Celsius. Again, at that point, it starts to boil, and it won't, it's at standard pressure, but it starts to boil. Once it starts to boil, remember it goes through an energy change, or a phase change, excuse me, not a temperature change. So let's now actually move into we're going to use this chart, and there's 5 baby Qs. Doesn't mean you'll use all of them, but all you're going to do is you're going to plot out what you're going to give me a chart showing me what the problem's talking about, and then you'll just deal with the baby Qs you have to work with. But there are 5 possible. So here's let me go for a little more information as I set up to this. I'm going to talk about phase change calculations, and we don't use enthalpy of vaporization or fusion. We use latent heat of fusion. It means the same thing. So as it says here, latent heat of fusion, L subscript F, the heat required to melt 1 gram of a pure substance at its melting point. And so I have the latent heat of fusion of water, 0 degrees Celsius. I also give it for copper. So everything's going to, again, have their latent heat of fusion and vaporization at melting and boiling points. And I will always provide these for you. So the molar heat of fusion, by definition, is the heat required to melt 1 mole of a pure substance at its melting point. For example, water. 1 mole of water. I have 1 mole of water. I go from moles to mass, and then I have my latent heat of fusion, which is grams per joule. My moles cancel out, grams cancel out, and up in joule. So it just tells me, again, my molar heat of fusion, how much heat is required to melt 1 mole of pure of my water. And it's shifting to the kilojoule. We actually move it, again, 3 decimal places to the left. The latent heat of vaporization, we also called enthalpy of vaporization, is the heat, or the latent heat of vaporization is the heat required to vaporize 1 gram of pure substance at its boiling point. So now this baby Q is mass times latent heat of fusion, or vaporization, excuse me. One before was mass times latent heat of fusion. But this one, again, this happens at boiling point. The value for water is 2,260 joule per gram, whereas copper, it boils at 2,595 degrees Celsius, and its latent heat of vaporization is 4,810 joule per gram. Again, those values will always be provided for you in a problem. Then specific heat, like I gave you back on that one chart, I provided all the specific heats for water, whether it's in a liquid state, whether it's in the ice, or it is a steam. So let's finally move into some problems. First problem says how much heat in kilojoules is needed to melt 250 grams of ice at 0 degrees Celsius. Now this is important you understand this. I'm starting at 0 degrees Celsius. Remember, at one end it's actually solid, and at the other end, at the right side, it's liquid. So I'm melting ice. I'm starting, when I say ice at 0 degrees Celsius, I must go through my phase change and actually literally melt it. So my mass is 250 grams, and my latent heat of fusion for water, or enthalpy of fusion, is 334 joule per gram. So my grams cancel out and end up in joule. But I want kilojoule, so I move it 3 places to the left. And heat, in order to melt, must absorb heat in order to melt, so it's an endothermic process here. I put a positive sign in front of it. Second example says how much heat in kilojoules must be removed. Now I'm going to drop down, so I'm from 50 grams of a molten copper at its melting point to solidify it. So it's a liquid now going, same thing, we're now in the same situation, but now we're going to go from a liquid back to a solid. So we're going to go through a phase change again, so it's mass times latent heat of fusion. My mass is 50 grams of my copper, and its latent heat of fusion is 205 joule per gram. And again, I always provide that for you. Again, we just simply multiply my grams cancel out in joule, but I change it to kilojoule. And now it's a negative value because now I'm changing from a liquid to a solid. I have to cool down, so I have to lose heat. As I lose heat, it's an exothermic reaction. Number 3, how much heat in kilojoules must be added to change 100 grams of ice at negative 10 degrees Celsius, there's a negative on the right hand corner there, into 100 degrees Celsius steam? So I'm starting at, as we plot this out, I'm sorry, the above number 2 is exothermic. As I plot this out, I have to show 3 values. My negative 10 is where I'm starting at, and then I have 0, which is melting point because I'm dealing with water, and then 100 is my boiling point. So first of all, I plot it out. My first baby Q I go through is I'm going from negative 10 all the way up to 0, and I'm going through a temperature change, so it's MC delta T. My second baby Q is now I must go through a phase change, so I go through latent heat of fusion, and then I'm changing from a solid to a liquid. Now once all of my ice is completely melted and it's changed to a liquid, then it's going to start to increase in temperature again. So I have another delta T, I have another temperature change, so MC delta T. But as I get up to liquid, I don't want 100 degrees Celsius liquid, I want 100 degrees Celsius steam or gas. So I must go through my last baby Q, which is my phase change here, changing from a liquid to a gas, and this is mass times the heat of vaporization. Now, the nice thing here, the mass given to your problem applies to all 4 baby Qs. The specific heat of ice is 2.06, the specific heat of water, liquid water, my second MC delta T is 4.184. The latent heat of fusion for water is 334 joule per gram. Latent heat of vaporization is 2,260 joule per gram. So everything's given to you except the delta T. So focus on the delta T. It's really easy. The delta T is only the temperature change for that baby Q. For example, my first baby Q went from -10 up to 0, and it went through a 10-degree change. Keep it positive. My second baby Q ran from 0 all the way up to 100, so it went through a 100-degree change. So it's a lot of busy work here. It's the sum of my baby Q's gives me the overall Q, and as I go through this, everything's going to cancel out and end up in the joule. Remember that grams and Celsius all cancel out. You end up in joule, but you have to realize I want the answer in kilojoules, so you move it three places to the left. It is a positive reaction because I'm moving up. So to move up, I'm getting warmer. I must absorb energy. So it's an endothermic reaction. My next one now deals, I want to talk about copper. And it says how much heat in kilojoules needed to vaporize 3.50 grams of solid copper. Penny, that's at 20 degrees Celsius. So my penny starts at 20 degrees Celsius. Now specific heats you needed for specific heat of liquid copper and a specific heat of copper as a solid. I provide them for you. So I have to count for my baby Qs. First baby Q, I'm increasing temperature until I get to 1083. So I'm going through a temperature MC delta T. At 1083 is a melting point. Now my copper starts going through a phase change. So it's changing from a solid to a liquid copper. Once all of my liquid copper melts, it then continues to rise, change temperature again. Now my energy is going to a temperature change, and I go up to 2,595. But I want vaporized, means I don't want a liquid copper, I want the copper in the gaseous state. So I must go through my last phase change, and so here's my fourth baby Q, mass times latent heat of fusion. So again, we have 4 baby Qs. The sum of my baby Qs gives me overall baby Q, or the overall heat or energy needed to vaporize 3.5 grams. So the nice thing, my mass is 3.5 grams in all 5 baby Qs. I gave you the specific heat of copper as a solid. That's your first MC delta T. Your second MC delta T, I gave you specific heat of copper as a liquid. Latent heat of fusion, latent heat of vaporization, I applied those. I've given you both those values in your notes, and on the test I provided for you if needed. So all you have to focus on is the delta T. So my first delta T started at 20 and went up to 1083. So you went through a 1063 degree change, and then you go second baby Q, or the second delta T ran from 100 or 1083 all the way up to 2,595. So you do all the work. You sum of your baby Qs, gives you your overall Q. But again, I don't want my answer in joules, I want it in kilojoules. And what I'm doing here, a lot of busy work with the math. Just look at the original values provided for you in the problem to figure out sig figs. For example, 3.50 grams, 3 sig figs, 20.0 degrees Celsius, 3 sig figs. I'm going to keep my answer at 3 sig figs. So it's positive because I'm getting warmer, so I have to absorb energy. This energy had to be absorbed to move from 20 all the way up to 2,595. So it's an endothermic reaction. Now I'm going to show you something that loves to show up on the test. Okay, we're not going to make it easy on the test, and well, some of it may be easy, but there's always a variable. This one's going to sound very much like our heat exchange problems when we take something hot, hot piece of metal, and place it in something cold. But we're going to actually pay attention to both sides. In this situation, and really that's what we're doing, heat exchange. But now the issue is we're going to go beyond just the regular between the 0 and the 100. So 1 is again losing the Q, and we're going to assume that all of the Q lost by 1 is gained by the other, and so that's how we're going to do this, make it equal. But you're going to need to plot out both substances. So here it reads, it says, in a lab, a student wants to experimentally verify the latent heat of fusion of water. So a student puts a piece of 0 degrees Celsius ice into 62.5 milliliters of water that's at 49.3 degrees Celsius in a styrofoam cup. It mixes it. The mixture of the water, right when the ice is completely melted, ends up at final temperature of 28.3 degrees Celsius. the final volume of the water is 76.0 milliliters. Now, in this situation, very, very important. Put a star by this. This is exactly what you do in the lab on Monday. This is exactly what you do in the lab on Monday. And so with this one, first of all, I want to calculate the latent heat of fusion of water, and then we'll do some percent air, and we will account for the differences. So that's, again, a key aspect. You're going to be doing this in lab on Monday. So we start out, we have heat transfer. So this is my heat exchange. So I'm going to plot out both my ice and the water, because both of them are doing something. So right now my ice started at 0 degrees Celsius ice. And so in this situation we know that I started out with my water was 62.5 milliliters. At the very end I ended up at 76 milliliters. So the difference between the two means my ice made up 13.5 milliliters of that, or grams, since it's water, density of water 1 gram per mil. So I know my mass, and I know my ice first had to melt. It's changed from a solid to a liquid, so that was this first baby Q, mass times latent heat of fusion. And then once my ice completely changed to a liquid, then it ended up cooling down, or warming up, excuse me, all the way to 28.3 degrees Celsius. So it went through a temperature change. It's MC delta T. Now that's going to be equal to the Q, overall total Q of my water. So the water in the situation, again, made up 62.5 mils or 62.5 grams. My water started out at, let me fix it. Sorry about that light. So the water started out at 23 degree or 49.3 degrees Celsius, and it actually just went down. So it actually dropped from 49.3 down to 28.3. So all it did with its on its side, it went through a temperature change. It went through an MC delta T. So with this, we assume that all the Q lost by the ice was absorbed by the water. That's our assumption. That's probably the biggest error that comes into play there, because a styrofoam cup is not the best insulator. In this situation, again, there's also human error involved with measurements. But in this situation, we plug in there what we know. I know the mass of the ice. We don't know its latent heat of fusion. When it changed to water, it's at the same mass. We know the specific heat of liquid water, and we know the delta T it went through. That's my ice. Is equal to my water. We know the mass of the water. I have the same specific heat, 4.184 joule, and my water went through at 21.0 degrees Celsius, the difference from 49.3 and 28.3. So now in this situation, my latent heat of fusion is my X, and we can actually solve for it. In the process, we end up figuring out the latent heat of fusion equals 288 joule per gram. Again, look for sig figs, look at the original values given to you in the problem. Now, percent air. In this situation, we know the latent heat of fusion for water is 334. So minus the observed, or the observed minus the accepted, either way, because you take the absolute value, it doesn't matter. And then you're going to divide by the accepted value, which is 334 once again. And then you multiply by 100, change it to a percent. We realize there's a 14% error with this lab. And you're going to expect a pretty good size error. Not too bad, not as bad as before when we did with burning the food, but you're going to get a good error. But again, if you can stay below 10%, it means you're doing it experimentally, everything's working out well. Next, let's kind of break it down and go through a couple of quick problems here. First of all, how much energy in kilojoules is needed to do each of the following? My scenario with A is I have 150 grams of ice at 0 degrees Celsius and change it into liquid water. Again, I'm starting at 0 at flat line, so I'm starting as a solid and changing to a liquid. All I'm doing is going through a phase change. So it's mass times latent heat of fusion. My mass is 150 grams, latent heat of fusion 334. 50,100 joule, and keep a positive 50.1 kilojoule. Yeah, I know there's ambiguity with the 150, but we'll just keep it 3 sig figs. Next, my 250 milliliters or 250 grams of water of 23 degrees Celsius, and turn that into steam. So I'm starting at 25, and I'm going up to a 100, which is my boiling point. But I'm going to go past my boiling point, because boiling point is still liquid. I want the liquid to completely change into a gas. So I have 2 baby Q's I have to account for. My temperature change, changing from 75 or 25 to 100, and my phase change going from a liquid to a gas. As I plug in my mass, the mass is the same for both of them, 250. I know my specific heat of water. I know the delta T of my water. I know the mass and the latent heat of vaporization, and I can actually solve for my Q. In this situation, again, we were moving up, so you should put a positive sign in front of it. Just like the last one, you're getting warmer, so you have to absorb energy to get warmer. The last one says we're going to turn 250 grams of negative 15 degrees Celsius ice into 135 degrees Celsius steam. Now, as you realize, we're going below 0 and above 100, so we're going to use all 5 baby Qs. So as we chart it out, there's only 4 numbers you need to show me: negative 15, 0 flat line, 100 I'm going to flat line, and then I'm going to climb up to 135. So what happens? First baby Q, MC delta T. My ice warms up to 0, and then begins to melt, goes into a phase change, mass times latent heat of fusion. And once all my ice is melted into a liquid, then my liquids goes through another temperature change, another MC delta T. Then it gets up to 100 degrees and it pauses because now it starts going into its second phase change at its boiling point. And all the energy is going into the phase change, changing it from a liquid to a gas. So I have my mass times latent heat of vaporization. Now once all my liquid is changed to gas or steam, then my steam or gas begins to increase in temperature again. So I have my third MC delta T. Now we know the mass for all 5 of these baby Qs is 225. That's easy. The specific heat of ice, 2.06. The specific heat of liquid water, 4.184. Specific heat of steam, 2.02. Latent heat of fusion for water, 334. Latent heat of vaporization, 2,260. So really how you're going after is the delta T's. My first baby Q's delta T went from 15 to 0, so it's a 15-degree change. My third baby Q went through a change from 0 all the way up to 100, so it went through a 100-degree change. And my last baby Q, last MC delta T, went from 100 up to 135, so it went through a 35-degree change. So as you plot all this stuff, you do all the busy work, and we see my lowest number, my value is 3 sig figs, so I'm just going to keep my answer at 3 sig figs. And again, I'm moving up, becoming warmer, so I must have absorbed heat. So it, again, put a positive sign in front of it. It is an endothermic reaction. Now I'm going to give you one more. That's a great example. This one loves to show up on the test. The first one we did with water, that's what you're going to do in lab. This one loves to show up on the test. So we have a situation that says we have 45 grams of a gas that's condensed into 445 grams of liquid water. This is important to understand right here. What's meant by this? Actually, the 445 was a combination of both the gas and the liquid. So my gas had 45 grams. And ends up mixing with my liquid to a total of 445. That means my liquid was at 400 grams. So a little understanding there. The wording's really not clear on how they state this, but loves to show up on the test, to be aware of it. So this liquid is actually mixed. The gas and the liquid are mixed, and the final temperature is 28.5 degrees Celsius is reached. Calculate the latent heat of vaporization of a liquid given the following data. So I show you the boiling point, the specific heat of my liquid, the initial temperature of the gas, and the initial temperature of the liquid. So first, just plot out. We're going to plot out what happens with my gas. The gas, first of all, we know has a mass of 45 grams, and we know the initial temperature of my gas started at 94.0 degrees Celsius, and according to the problem, it ended at 28.5 grams or degrees Celsius as a liquid. So what you must understand, you have 2 baby Qs you have to go through on the gas side. First, I had to change from a gas back to a liquid. Then as a liquid, it dropped back down to 28.5. And we know it was a gas at that point because the boiling point was at 94 degrees Celsius. So it started as boiling point. For the water, it is 400 grams. Combination 400 plus 440 or plus 45 gives me 445. My water in this situation, initial temperature was 10.4 degrees Celsius, and my final temperature, it just went up to 28.5, so it went through just an MC delta T. So I have the mass of my liquid equals, the Q of my liquid equals the Q of the gas, and so you have to add up the baby Q's on both sides. My only unknown in this one is actually the latent heat. According to the problem, I'm calculating the latent heat of vaporization of the liquid, so it's on my right hand side. Now my water, 400 grams, I knew the specific heat of the liquid, and I know it's delta T. The mass of my gas started at 45 grams. I'm going after latent heat of vaporization. That is my X. But then when I MC delta T, pay attention to this. I have the mass here, but now it's into the liquid. So I'm going to assume the density of the liquid, and then I'll just calculate the delta T, which is the difference between 94 and 28.5. Again, my X is my latent heat of vaporization, so I just have to isolate X. It ends up equaling 204 joule per gram. I'm not going to put a positive and negative in front of it in this situation just because I'm going after a value which is a positive value.